and algorithm lecture 2 on asymptotic notations. You are able to view it on my screen. That's our agenda. Asymptotic notations and the different types of it, like big O notation, omega notation, theta notation. And we discuss about this asymptotic notations with an example, like how we actually calculate them using divide and conquer algorithm. And in order to understand about how we are calculating this asymptotic things with divide and conquer, so we need to understand about another interlinking topic called as recursive, as well as another one called as master theorem. So these are the connective topics in order to take an example related to your asymptotic notations. Let's no need to wait. Let's go deep into this particular topics. Now, before getting into this particular asymptotic notations, what actually is an asymptotic notation is, let me just draw a simple equation. So for example, there is an equation called as n square, or this number can be 5n square plus 10n plus 3000. There is a value like 5n square plus 10n plus 3000. Now, in order to calculate this particular equation, now here the purpose of asymptotic notation is to understand the growth rate. That is very important. Every time whenever you are using an algorithm or whenever you are writing an algorithm, so one of the very important element is, so for example, if you are giving value 1, is it able to do it in a least amount of time? That's not our major priority. Even in our first lecture, we discussed about it. What is the scalability of it? Now, when you are writing an algorithm, when you are increasing this n value, means the number of value when you are increasing. For example, when the calculation is only 1, it is easy for us to calculate it. But when the value is increasing, for example, you have n square, which is an exponential notation. When you are having this n square, to calculate this n square, so your algorithm take a lot of time. Means in order to calculate it takes a huge amount of time. So the purpose of your asymptotic notations is in order to calculate the growth rate of a function. So in order to calculate the growth rate of a function, when you are looking into this entire equation, 5n square plus 10n plus 3000. So whenever you are taking this 10n and 3000, so even though you are increasing your n value, it may not take a much time in order to calculate 10n and 3000. Why? In the sense they are going in your linear rate, they are trying to go for it. That's the reason, even though you are increasing your n value, it may not increase the time complexity in order to calculate this particular function. But when you take this n square, in order to calculate the particular, or in order to do an operation, for a increasing n value, it takes a huge amount of time. So now the function of n, so the complexity in this entire equation is this 5n square. So now the function of n is equal to your 5n square. Now the goal here is, what is the worst amount of time and the least amount of time it takes in order to calculate this particular equation is very important. Means as you are increasing your n value, means the growth rate, as you are increasing your n value, what is the least amount of time? Every time. So as a programmers, or as we are doing our algorithms and all this, we need to be very particular about two things. One is our input size. Let us take, this is our input size and this is our time. So as the input size is increasing, the amount of time it has taken in order to complete the task need to be as minimal as possible. For example, as the input size is increasing, your time is also increasing. We can't call it as a scalability. And as a effective programming, or as an effective programmer, our goal is like, we want to reduce the time, we want to reduce our memory, and we want to improve our scalability. Now whenever your input size is increasing, the time it has taken in order to complete a task, if it is increasing, there is no point with it. Now here you are able to see on the left hand side the asymptotic rates. So the growth constant, for example, if you are able to take a constant growth, what exactly it indicates? Or before going into a constant growth, we can look on to a factorial growth. What actually a factorial growth is? As your input size is small, so in order to execute, or if it is taking a huge amount of time, it is under your factorial growth, which is theta of n factorial. So in order to calculate a particular function, how exactly we calculate a function is in lines of its running time on the complex things. Now if you take this entire equation, we need to calculate the running time of our function. Why? In the sense, even though the n value is increasing on the zones, it may not take much time. You don't actually find the difference. But the most of the time consumed in order to handle this entire function is taken at this 5n square. That's the reason, in order to run this 5n square, what is the running time? We are indicating the running time as theta. Now, in order to understand, as your input size is increasing, what is the amount of time it has taken? If it is in a factorial growth, it takes a huge amount of time in order to complete a particular task. The running time of the function going to be more, even with a smaller input size. So when your function is in a format of your constant growth, even though the input size is increasing, there may not be huge amount of your running time, which we can call it as your constant growth. And in this way, we got our logarithmic growth, our linear growth, our superlinear growth in this way. So when you are taking this asymptotic rates, as you are starting from the constant growth towards your factorial growth, so the functions which are in constant or logarithmic format and all this, they're going to have the good performance, means like they're going to have a least amount of running time, or we can say the least amount of time complexity. And when you're going towards exponential growth or factorial growth, you can see here 5n square, which is in a factorial growth format. It takes a huge amount of time. Even for a smaller inputs, it's going to take a more amount of time, the factorial or exponential. So this is going to be bad or worst in lines of our time complexity. So apart from this asymptotic notations, we have three types of it, as we discussed. One is worst scenario, another one is best scenario, and another one is even more, we can say like average scenario. So whenever it is going to be like worst scenario, means like we are expecting, if we take in lines of our data structures and algorithms, I just want to learn DSA. In order to learn DSA, how much time I'm planning? For example, I'm planning to learn data structures and algorithm within 1 month of span. But the time complexity increases. How exactly the time complexity is increasing? Based on the size of it. Means the more and more content is getting into your brain, the complexity to digest all this information takes into the picture. So now, normally, what is the best scenario? You can complete it within, or average scenarios, you can complete DSA within 1 month. But because of the more time complexity, what is increasing is, so you are not completing DSA within 1 month, you are trying to complete it in 2 months. So before going into the DSA itself, preparing for the worst scenario, best scenario, and even an average scenario is pretty good. Why? In the sense, I will be knowing if I am able to complete DSA, I can complete it in 2 weeks, or I can complete it in 2 months, or even in a best, I can complete it within 1 month. So by understanding these 3 levels, I will be prepared for it. Even while you are writing a program, if you are able to understand the worst scenario, how much huge amount of time it's going to take in order to complete a task, if we know it, that's going to be even more precise. For that reason, we got 3 notations. One is your big O notations. Let's go through it. This is called as our big O notation. So what we are trying to do is, I'm creating a function f of n, where exactly you can see your function, your f of n based on the example can be your 5n square. And g of n is a function which you are trying to create it. For example, your g of n can be something like 7n or something. Some function I'm choosing it, some n function I'm choosing. So, or you can just choose n or whatever it is. So what exactly this condition speak about is like f of n is less than or equal to c of g of n, where c is your constant value. So what exactly this big O notation is speaking about? The function of n is less than or equal to c g of n. So what exactly this is speaking about is the time taken in order to run the basic function of n is lesser than or equal to your g of n. Means like the time taken in order to run this particular function is greater than whatever you are running it. Means like in a very simple note, the worst case scenario means you are expecting to run an for example, here on the x-axis is your input size. This is this is our input and this is our time complexity. Now what exactly it speak about is, this is the average time which takes for a function to complete the overall task, or the runtime of a function is f of n. But what exactly Cg of n is, this going to be the worst scenario. If this is like you are able to complete your data structures and algorithm within 1 month, this can be your 2-month span. So by knowing the worst span of time, okay, this is going to run at this up to at this level, means whenever you are writing an algorithm, you are testing even the worst scenario as well, at what level of time it is going to take if the size is increasing. By understanding it, you are understanding the scalability of it. Whether seriously clients are okay to go for our algorithm to take this much amount of time or not, we are understanding. So we are always taking the feedback from the client. Based on that levels, we are making sure whether it is going or not. Why in the sense, every time, for example, when you are working for a Facebook, or when you are working with a Google, or when you are working for any big things, so they want to complete the task in as less time as possible, even though the size is increasing. For example, I want to increase my size, but the time need to be less. But how can you measure it? You can't just give a guess. So I have written this particular algorithm, or I used what is a linked list, or I use this particular bubble sorting, or I use this particular sorting, so it going to take least amount of time. You can't give something in lines of guesses. So you need to calculate it in lines of mathematics, and you want to showcase them the 3 levels. So if you are running it in an average, this is the time it going to take. What is the average time? F of n. So what is the worst scenario? C g of n, or we can call it as big O notation. Or it going to take even the least amount of time, not even the average, even the lesser time. It going to give the best performance as well. Within a short span of time, even it can complete the task, which is your omega notation. So now the purpose of all these 3 notations is, whenever you are designing an algorithm, or whenever you are writing an algorithm, you are calculating it, and you are being confident to showcase that to your client or to your vendors, or you are being confident if someone is questioning you. For that reason, calculating this is very important. And before going into, we can have a look over omega notation. If you are able to see the omega notation, this is what we are able to see it. So the f of n going to be again average time it going to take. Again, this is going to be your average time, like 1 month, in order to complete your data structures and algorithm. What is Cg of n is maybe like within less than 1 month, or we can say in 2 months, or in 2 weeks or 3 weeks, you can complete DSA. That is the best performance. So, but best performance we don't much care about. Why in the sense, we don't want to cross beyond that worst performance. Why in the sense, when the data is increasing more, that is our major challenge. When data is increasing, we need to be prepared for the worst scenario. So that is very important. So big O notation is comparatively more important than your omega. And in order to understand the upper levels and the lower levels, in order to check the upper levels and the lower levels, you can use your theta notation. So this theta notation going to be this theta notation going to be this f of n going to range between, which is f of n is less than or equal to C2 g of n. So this is our upper bound. So this upper bound is higher than your f of n, means this f of n is less than our upper bound, and this c g of n is lesser than f of n. So c1 g of n, this function is less than or equal to your f of n. This is the condition which we are going with. This is for our theta notation. These are the 3 conditions we are trying to calculate. So Kant, if we are able to go with an algorithm, how we actually do it? The theoretical wise, it's okay. For example, what is the purpose of an asymptotic notation is like in order to understand the growth rate, means what is the time it has taken when the growth is increasing, means like when the input size is increasing, what is the time complexity of a particular function. In order to understand, we are going for it. In order to compare between algorithms, which algorithm is good for a particular task, yes, you can use your asymptotic. Now let's take a small example like our divide and conquer algorithm. Let's see. Yeah, so before going into divide and conquer algorithm, there is one basic theory. What exactly divide and conquer algorithms speak about is like if there is a data. For example, if there are values 7, 8, 6, maybe they are in sequential format. I'm just making it 3, 8, 9, 6, 5, 1. So this is the data which we have it, and we have the number of elements is like 6, n equal to 6 elements we have it. Now this is related to the sorting. Now when the n size is increased to like 200, again the time taken in order to sort it increases based on the function you have written. So even while you are sorting it, we need to be very precise about even the number of elements increasing, the sorting time need to be the same. For example, if it is taking few seconds, even the sorting time for 1,000 need to be the same, 1 lakh need to be the same, 10 lakh need to be the same. That is very important. So how we can measure whether we are maintaining the same time or not? Using asymptotic notations. Now what we do in a divide and conquer is whatever the 3, 8, 9, 6, 5, 1 we have it, we are trying to split it by 2. 2 parts I'm trying to split it. So 3, 8, 9, 6, 5, 1. So 2 parts I have split it. And even this 3, 8, 9, 6, 5, 1, again I'm trying to split it into 2 parts. So as 3, 8, as 9. And even this 2 as something like 6, 5. And this one as 1. And again this 3, 8, I'm splitting it again into 3, 8. And again the 6, 5 I'm splitting into 6 and 5. So what I'm doing in this entire divide and conquer is whatever the data I have it, I'm dividing it by 2. In this way, I'm going to finally last values. And what I'm doing is whatever I divided it, now I'm trying to conquer, means like I'm trying to sort them, all these sub problems, and I'm trying to combine them. That is the concept of our divide and conquer algorithm. So what exactly we do in lines of divide and conquer is, in the conquer stage means you splitted your problem. So each sub problem is solved with a recursive function. What is a recursive function? If a function is able to call its own function, we call it as a recursive. So if it is able to call the same function within the same function, we call it as recursive. So why we basically use recursive? There are bunch of advantages. One is like when there is a complex task, you can divide it into a sub problems and you can solve them in a more simplified way. For that reason, most of the time we use a recursive. Even in the divide and conquer technique, so we are dividing it while we are trying to conquer, we are trying to use our recursive functions. So whatever the function you define, the same function you call it inside it, so that you are able to simplify the task of a complexity and you can achieve it. And even apart from it, the code going to look even clean and even more professional. For that reason, even some people go and knock the door of the recursive. And while you are trying to achieve a task, if the task is so simple, no need to write a recursive, you can just directly write down a normal tasking. But if the task is complex, yes, you can choose your recursive thing. So here you are able to see the same recursive function, what you are doing. Now I want to calculate the factorial of 6. Now what exactly your factorial of x going to be? It's going to be 6. So this value going to be checked for this condition. Is 6 equal to 1? It's not. So this condition is not getting passed. Then what it is doing? It is passing through the else condition. So what is your x value? 6. And what is your factorial? It is 6 minus 1, which going to be 5. Once it completed, again this 5 going to be passed to this. Again, it going to be checked in this condition. Is it true? Not exactly. Again, it is getting multiplied at this point. Again, it is checking this condition. In this way, it is keep on calling the same function of its own until it completes the task. When it going to stop? When your x value is like again now 4, 3, 2, 1. Again, if x equal to 1, return 1. Finally, it is returning 1 and it is stopping it. That's what we are doing with this particular recursive function. Now, when we have this recursive function, in order to calculate the time taken for each subproblem, now what I need to do, I can't calculate a complex problem timing. Now I want to calculate the timing for each subproblem. Means I want to calculate a time for each recursive problem. In order to calculate a time for each recursive problem, we need to use one mathematical technique called as master theorem. This is our master theorem. Based on the master theorem or master method, this is the equation of our master theorem, which is T of n is equal to A T n by B plus f of n. So what exactly this equation states that here T of n is the time complexity or the running time we are calculating for each subproblem for a particular recursive thing. So based on asymptotic bounds, we are trying to generate three scenarios. What are the three scenarios? Worst scenario, average scenario, and even the best scenario. Best scenario in the sense taking a least amount of time. Average time is f of n, and your worst scenario going to be it is taking a more amount of time. So now you are able to take this first condition. What exactly this first condition speaking about? If f of n is equal to, so big O notation, n log b a minus e, epsilon in the sense here a constant value. So then when we need to go for this condition, so now whatever the complex problem, the time taken in order to run each and every sub problem is increasing. For example, now you are going with a divide and conquer algorithm. What is the idea behind it? You are having a complex problem, you want to split that problems into sub problems. Why? It's going to take a least amount of time. But after splitting it into sub problems, as you are doing or calculating or running this function, the time complexity is increasing. If the time complexity is increasing as the sub problems are increasing, then we are going with our big O notation. So then what exactly your T of n going to be? Theta is like running time of n log BA. In case what is the second condition is if the running time, so whatever the time taken in order to run a function is remaining average, it's more or less equal. So then what exactly happens? So between the sub problems, as it is going towards the sub problems, if the running time is more or less remaining same, then we need to go to the second condition. If it is same, means like average condition. But when you are going into your omega condition, what exactly omega states about? So as you are going across multiple sub problems, so the time taken in order to complete the task is reducing. Then you need to go for your omega condition. So now when you are getting into divide and conquer, so what exactly the purpose behind it? As you are going to the first level, you are having more values, means like more time complexity you are having. The second sub problem, lesser more time. Third sub problem, even more lesser more time. So as you're going towards the sub problems, the time complexity need to reduce. Means you need to go to your last value based on this particular equation you are trying to calculate your f of n. So how you take your a value going to be the size of your particular, so how you are splitting it, the number of parts you are splitting it, whatever the problem you have it, you are splitting your problem into two parts. So where a going to be 2. And what is n by 2? The size of your particular sub problem. You are splitting your entire problem into half the part, so which is n by 2. And we don't know f of n, so from this equation we are able to calculate our f of n. So this is what you are able to get your f of n value. So in this way we are trying to use, means like I'm not going deep into the calculations of it. So while we are going to the above classes or the next classes, we will be discussing more use cases. So now I used asymptotic notation only, how exactly we calculate it using a divide and conquer technique. In this way, when we are going into the future, we can take two different types of algorithms, we can compare them, we can calculate this asymptotic notations manually, and we can understand it, and we can decide how we can deliver it or how we can draw some insights while in a real time point of it, so we can just discuss about it. And in case if you like this content, please do subscribe to my YouTube channel, and thank you so much for these lectures.